just an example, we're thinking it could be a function of several variables. We could think that's something like, I'm looking at a table here in section 14.1. It's got one of the wind chill table, but we could think of that, the air temperature, like wind chill index is a function of what? Air temperature, but also what's the other variable? Yeah, the wind speed, right? And that's what we're saying. I mean, we can look at just situations like that is what we're talking about in section 14.1, where we're going with functions of several variables. We're saying, okay, the wind chill index would actually give us, okay, that's a temperature based on like the air temperature, but also the wind speed. So many examples in this scenario. So, and we've got to copy the worksheet just so it makes it easier to work so many problems in class. But I'm going to write one like the first one. We used to do what? Function of x equals x squared plus 2, previous to this section. What letter is f of x?
Y.
Y, okay. But y is only a function of how many variables?
1.
1x, right? So today we're going to see stuff like, well, z equals something like cosine of, I'll write this first one down, what? Cosine of 4x plus y. All right. So now the z is composed of two variables, x and y. Now how can I write the f of x here? The f of x doesn't work. But the notation we can now use is z is a function of x comma y. So we can write z as a function of x and y. This is multivariable functions. We can write z as a function of x and y. And surely we get in the problem we go, something's a function of x and y and w. All right? But that's the notation we now can use. We just put a comma between the two variables that this z is a function of. Okay? Well, to start out with, because we're talking about multivariable functions, this being a function of x and y, we should look at things like domain and range. But always remember, f of x, y, can't you think of f of x comma y as z? Like the z-axis. You can think of this geometrically in all these scenarios. So in this first problem, that's what I want to ask for. Let's express the domain of this function. What's the domain of f? I noticed on this sheet they called it g of x and y, but I'll just keep this f as y. What's the domain of the function f? Previous to multivariable functions, domain, we only thought of x, didn't we? Now domain is what's going on with x and y. What's going on in the xy plane? What's going on with the variables x and y? That's what we're thinking about for domain. So what's going to be range? What's the other letter? Z. Yeah, the z. So when z will be, we're going to be thinking about the range. Thinking like three-dimensionally. But your domain is just what's going on with x and y in the problem. So when you and I got to look at this problem carefully, we know about trig functions, cosine. Domain of f. What is x and y allowed to be? Relationship with x and y in two-dimensional space. Is there a limit to it? Very good. Can't x and y be anything? Can't you get the cosine of 1,000 degrees and the cosine of 0? That still exists. There's no like weird things in here. So the domain of f is actually, all real values. Now, if you wanted to put the r thing right, you want to do this, then can't we do something like that? Because we're thinking what? All x's and y's are allowed to be. If I graph the x and y values, like make a graph of this, well, we're saying it could be all points, all x and y coordinates, all pairs in two-dimensional space. So wouldn't I be shading everything? This is my domain, and all these points. And that's what we're saying. So it's all x and y, it's all real numbers. Feel free to just do this. The range is a different story. What's the range of this function f? Okay. What do we know about cosine? So now we're thinking about z. Z equals cosine. What's the highest cosine ever gets to?
-1 to 1.
The highest is 1, the lowest is -1. So there's our range. This has a limited range. So the range we're thinking, what's z allowed to be? But domain was what's going on with x and y. Okay, you can think of the xy plane. So the range, I'm just going to write -1 to 1. Cool. Well, can we look at another example? And in this time, everyone, we're going to sketch the domain. So let me go to the next problem. It's the function f of xy equals, I've got the natural log of 4 minus x squared minus 4y squared. The directions say, find and sketch the domain. So we don't need the range. They just want the domain. So this is where we start in 14.1. We need to talk about functions of several variables. And we're talking about functions maybe we can graph three-dimensionally. We should be thinking about, well, what's its domain, what's its range? Find and sketch the domain. That's what's going on with x and y, true? So our focus is this. This 4x minus x squared minus 4y squared. So for domain, I'm thinking, all right, what can x and y be? And then we'll sketch it. We'll sketch it in the xy plane. Okay? So for domain, what does x and y be? Anybody know about natural logs in this parentheses?
Greater than
Can
0,
it be
right?
negative? So
No,
it can't be negative. Can it be 0?
no.
It can't be 0, can it? Natural log of 0 is undefined. Right? Hey, keep in mind, because you might see a problem with the square root. Square root can't be negative. Like square root of -1, that's not real. But can you get the square root of 0?
Mm-hmm.
So yeah, you can get the square root of 0, but you cannot get the natural log of 0. So this is what I'm going to write. For my domain, I'm first going to find it. I'll start with this. Oops. 4 minus x squared minus 4y squared must be greater than 0. I'm not putting an equal sign in because of what we just discussed. But if that was a square root here, you could have put a equal sign. I just wanted to show that to you so you go, oh, a problem with the square root there would be quite similar. Okay, there's my domain. Hey, can we rewrite this? Because it has x's and y's, and just get the constant over here. I'll do that. I'm just going to subtract 4 on both sides. Now, I don't like all those minuses, so I'm going to get rid of all the negative values. So I'm going to multiply -1 on both sides. Do I have to do anything with an inequality?
Yeah, you could change the sign.
Okay, so if I multiply -1 on either side of an inequality, I switch the direction, true? So I've got x squared plus 4y squared is less than
4.
4. There's the domain. We just described the domain. There it is. No leeway. That's a written expression of the domain. All x and y coordinates such that x squared plus 4y squared is less than 4. But in this scenario, it's kind of hard to really understand that domain, so that's why we sketch it. They wanted us to sketch this domain. We're going to sketch it in the xy plane. How do I sketch that? Is that a circle?
Yes.
X squared plus y squared equals 4 would be a circle. See, the less than means we'll just shade inside it, whatever this is. Right? We'll just shade inside it. That's not a circle. X squared plus y squared equals 4 is a perfect circle. Does anybody know what it would be? It's kind of like a squish circle. What do you call that? An ellipse. And the easiest way to sketch an ellipse, everyone, think of that with an equal sign. The easiest way to sketch an ellipse, I'll put the equal sign now just so we can sketch the actual curve, is the easiest way to sketch this ellipse here is use intercepts. So I'm going to start with x equal to 0. X equals 0, hide that. What's y equal to?
1 plus minus 1
So y can equal 1,
or negative
or
1.
y can equal -1, right? Let me get 2 easy points. Now, let y equal 0. What if y is 0?
Plus minus 2.
Also minus 2. Alright. Sketch your ellipse. Curve. And when we're sketching the domain of that multivariable function. the function of x and y? Where do I shade?
In between.
Because it's less than, I shade inside. There it is. This is negative 2. If you want to label these, that was 1, that's negative 1. It's not a rectangle. Sometimes on tests I get a rectangle. It is not a rectangle. Right? That's the domain. Cool. Now if you're curious about the range, I know I didn't ask for that. Natural logs, a range, it could be all reals, couldn't it? Right? But the domain, x and y, couldn't go outside of this. So think of that three-dimensional graph. You're like, oh, it'll all be kind of squished in there. Okay, anything else I should do because it didn't have the equal sign? Back in your inequality days, what should I do at the edge of that curve? Dot it. So I'm just going to dot it. I'm dot that curve because it didn't have an equal sign. So it's the set of all points inside of this ellipse, but not on the edge of the ellipse. And there's our sketch of the domain. Cool.
There's a positive 2, right? On the
Oh, you're the best.
x-axis.
A little dash makes it look like a negative.
Yeah.
Thanks, Art. Negative 2 to 2, negative 1 to 1. Thank you. Excellent. Hey, just so you're curious, because I think I have one line of problems up like this. What if this just had, you know, x plus y plus 1? Well, then the x plus y plus 1 would have to be greater than what? 0, right? Okay. And then you'd have to sketch something like that, right? Well, what does that sketch look like? That's not an ellipse. I heard it's a line. And where do you shade? You shade above the line or under the line? It depends. If it's y what? Greater than something, you shade above it. If it's y less than, you shade below it. True?
Mm-hmm.
Just make sure. In that case, you just have a line. Maybe it's going like this. Maybe the line's going like this. But you shade everything above it, or that would be it for me. Nice. All right. Over now, I want us to do. I mean, we're going to work this problem that I have here. Sketch the graph of these are problems just from section 4.1. 8 minus 2x minus 4y. This is going to become rather important throughout the remainder of this chapter 14 here. Even in chapter 15 and chapter 16. We're going to have to sketch this thing. So first of all, what letter can I call this? I'm not talking about just sketch the domain. We're talking about sketch the graph.
Z.
That's z. So you can say the function of x and y is z here. Okay, so I'm going to get ready and put the x-axis, y-axis, z-axis. The positive y-axis. This is the positive x-axis. This is the positive z-axis, right? I do want to point out some students do like to show how, okay, there goes the negative x-axis. They extend that. This is up to you. And there goes what? The negative z-axis. And there goes the negative y-axis. And you just want to put a little bit more into it. A lot of times you'll notice I'll just go up, for all the positive axes we have. Okay. So z equals 8 minus 2y, 2x, whoops, sorry, minus 4y. I'm going to rewrite this and put the x's and the y's and the z on one side and keep the 8 on the other side. So I have 2x plus 4y, if I had 4y on both sides, plus z equals 8. Isn't it the same equation? Does anybody recognize this from the last chapter? What this should be? It's got no x squareds. It's the equation of some surface. That is not an ellipse. Right? Ellipsoid. This is not a sphere. It's not a paraboloid. There's no squares on any one of the x, y's, and z's. That's a flat out what?
Plane.
Plane. That's just a plane, isn't it? Right? And if you're curious, that 2, 4, 1 is the normal vector to the plane. Remember that?
Mm-hmm.
So we're going to really begin sketching a plane. The easiest way to sketch a plane is by the intercepts. I mean, it's going to look like a triangle. That's what it's going to look like. So I can use these negative y's, x, negative z. I might take this off so you can really kind of focus on it. Let's use the intercept method. So pretend x and y are zeros. What would Z have to be in this problem?
8.
We need 2 more points. I'm getting the intercepts, like the x-intercept and the y-intercept and the z-intercept, just like I did the ellipse.
So
Cool.
X will be 4.
Pass that back. There you go. In case you want to write on that. All right, what if x is 0, z is 0?
2.
1 more intercept. What if, what's left?
X is left.
And x is a, we're going to plot all these, connect them,
4.
but it will look like a triangle. So if you don't want to have these, that's okay. Like in my setup here, my 3-dimensional graph, let's see, 1, 2, 3, 4, 5, 6, 7, 8, put a dot. 1, 2, put a dot on the y-axis. 1, 2, 3, 4. The reason I raised those negative axes is because I didn't have any negative values here, did I? That's right. Another way. And we just connected. This is just a portion of the plane, but it's a nice sketch of the plane. That's a nice sketch of the plane. That's something you'll do often in this chapter. In the next chapter. Especially chapter 15 and 16. You'll find yourself making sketches like that. Imagine making a solid out of this. Imagine taking that flat plane, that ramp that's coming down there, part of that flat plane, and then putting some sides where the sidewalls are the XY plane, the YZ plane, the XZ plane. You can build a solid out of this. And think of the solid, they call it a tetrahedron. Is that okay with that? All right. What about this one? We've done this before, but I wanted to do it again. Because this problem is in section 14.1. They said, can you just sketch this? I did this once at the very end of class one day, when we just learned about